All right, here we are at the final section of the chapter, our proof chapter. It's called Indirect Proof. This is proof strategy. It's a way to structure proofs, though similar to a way that we've seen before, is in a certain regard very, very different. Okay, but it's also extremely important. It's not a mere convenience that we have. This is something that we absolutely must have. And the basic idea behind it is this, is that we will prove that a certain statement must be true because we will find its negation, that is, its denial, cannot be the case. Okay, that its denial cannot be the case. So what we'll do then is we'll consider its denial, we'll consider its negation, and then we'll show, and what looks very much like the proofs that we've done, that that cannot be true. And then we'll conclude that the proposition, the statement that we wish to prove, is in fact true. That's just, of course, sort of a general outline of what we hope to do. So let's look at particular examples of this. So the first of these comes from my son. Some years ago, he's now in college, a junior, as a matter of fact, as I speak. But many years ago, he was probably 6 or 7 at the time, I heard this voice from the back of the car say something like this. I mean, I've cleaned it up just a little bit to make it clear, but he did have exactly this idea. Well, here's what he said. There can't be an opposite day, he said, because if there were, it would be the opposite of opposite day on opposite day, since everything is opposite on opposite day. But the opposite of opposite day is, of course, normal day. So if there were an opposite day, it would be a normal day. But that's impossible, right? Do you get the point? What he wished to prove is that there cannot be an opposite day. And how did he prove that there cannot be an opposite day? Well, he said, suppose that there is an opposite day. That's what makes indirect proof the kind of proof that it is, because one supposes that what one wishes to prove, one assumes for a moment that it is not true, and you ask yourself what follows if it is not true, and then you find that something impossible follows. Okay, so let us suppose for a moment, let us assume for a moment that there could be an opposite day. Well, that means that it would have to be the opposite of opposite day on opposite day, because everything is opposite on opposite day. But the opposite of opposite day is a normal day. So if there were an opposite day, it would have to be a normal day as well, and that is impossible. So how do we know that there cannot be an opposite day? Because we have been able to prove that it's impossible that there is. Okay, this is the nature of indirect proof. So I've got a certain way to structure this, so let's talk about that. So here's the structure of the proof and the way that we will structure all proofs of this variety, so-called indirect proofs. We state the conclusion that we wish to prove. There can't be an opposite day in this case. Then we assume the opposite, not because we believe it, and not because that's what we'll finally conclude, but instead to show ultimately that it cannot be true. So assume the opposite. That is, there can be an opposite day. That's the opposite of there can't be an opposite day. Then explain why this assumption leads to a contradiction. Opposite day would also be a normal day. That's the contradiction that follows if there could be an opposite day. And then, of course, what this means is that the original assumption is false. If the assumption leads us to a contradiction, if it leads us to assert something impossible, then it must be false. So the assumption was there can't be an opposite day. That has to be false. So it follows that there can't be an opposite day. So let's have some names for the parts of an indirect proof. Okay. Now, this is something we'll do here at the start to try to help you understand the structure of an indirect proof. This is something that likely will drop later on, but here it is at the start. First of all, we have given and prove, because it is a proof, and every proof, no matter how it's structured, has the given and what it is that we're supposed to prove. And then we have an assumption. And in that assumption, we assume the denial or the negation of what it is that we wish to prove. And then in the reduction, we prove that that denial leads to a contradiction. That is a statement that is impossible. And then in the conclusion, we of course say, well, since the assumption leads to this impossible consequence, it must be false. But since the assumption was the negation of what we wish to prove, and since it's false, what we wish to prove is, as a matter of fact, true. Okay, so contradiction. What do we mean by contradiction? Well, what could we contradict in the reduction part of an indirect proof? Anything that we know is true. So if we contradict a postulate, there you go. If you contradict a definition, if you contradict a theorem previously proven. And of course, another possibility is this, is that you contradict the given of the proof. itself. I mean, for that proof, that is something that we know. It is given. Okay, so if we find that we have to contradict the given, then yeah, but we have our impossible statement. Okay, so let's look at a couple of more examples, and I'll talk you through these. And then the problem set, I also attempt to guide you through. I don't just say at the start, create indirect proofs. I do most of the work for a number of indirect proofs for you and simply have you fill in blanks. So I think of this as a gentle introduction, but it is important. And by the end of that problem set, you will be asked to prove a couple of results, official results that are on uh, the theorem sheet, the theorem handout, okay, in the indirect fashion. Okay, so prove that if n squared is odd, then so is n. Okay, of course, n is some number. So prove that if n squared is odd, okay, and so is n. Oh, okay, so the given is that n squared is odd. The given is always what comes after if. We're supposed to prove that n is odd. That's the conclusion. It comes after the word then, as always. So this is an indirect proof. So that means we have an assumption. What is the assumption? The denial or the negation of what we wish to prove. So we wish to prove that n is odd, so our assumption is that n isn't odd. And again, this assumption is not, we don't say it because we believe it or we'll hold it at the end. Instead, we just simply want to consider it, okay? And in fact, what we mean to do is to show that a contradiction follows from that assumption. Okay, so we've said that n isn't odd in the assumption. So if it isn't odd, it's even, of course. But what do we know about the square of an even? If you square an even number, of course you get another even number. So it follows now that n squared is even. Oh, but that contradicts the given because the given says that n squared is odd. So the assumption leads to a contradiction. And what does that mean about the assumption since it leads to a contradiction? It's false. True statements can't lead to contradictions. So it's false that n isn't odd, which means that it is. Okay, which means that it is. So here's another one. And this begins to look a little bit like the proofs that we'll actually do later on in the class by means of the indirect method. So let us prove that if angles A and B are supplementary, then not both are obtuse. Okay, well, let's see. The given here is that angles A and B are supplementary. What we wish to prove is that not both are obtuse. Also, we'll do this indirectly, so that means we make an assumption. The assumption is the negation of what we wish to prove. And the negation of not both is, of course, just both. So the assumption is that both A and B are obtuse. And then let's think about what follows. Obtuse angles have a measure greater than 90 degrees. Thus, the sum of A and B is greater than 180 degrees. If you sum up two quantities, each of which is greater than 90, then the sum must be greater than 180. However, this contradicts the given, for the given says that angles A and B are supplementary, which means, of course, that their sum is 180 degrees. So the assumption, which was that both A and B are obtuse, leads us to contradict, in this case, the given. Okay? Doesn't, again, matter what you contradict. Just if you contradict anything you know is true, that's what the reduction has to do. Okay, so since that assumption has led to a contradiction, it cannot be true. It cannot be true, that is, that both A and B are obtuse, which just is to say that not both A and B are obtuse. Okay, so there we go. That's your quick introduction to indirect proof. And we've got a good problem set for this, so go take a look at that. And we will work on that problem set for a number of days. Some parts of it are fairly straightforward, I think, but some are subtle and difficult. So I'll definitely give you a number of days to work on that, and we'll talk about it quite a bit. And it will culminate in two important results, actually one more important than the other, official results, as I said. One is that two lines cannot intersect at more than one point. Okay, that'll be a theorem. And we'll also prove the converse of the vertical angles theorem. Okay, and I won't take any time here to talk about what that would be. You might think about that for just a moment, but we will prove that the converse of the VAD is true, and we'll do that indirectly.